So I mentioned already, right, what is the purpose of the capacitor? Capacitors store energy, okay? And they store electric potential energy. So we're going to kind of analyze the capacitor now in terms of energy. So the way that we charge up a capacitor is we plug it into a source of constant potential, like a battery or maybe a power supply. And getting those charges built up on the plates, it requires work. And this work results in electric potential energy being stored in the capacitor. If we don't change anything after we charge it, that charge and that energy will just sit there until we discharge it and connect it to something else in a circuit. Okay, and the discharge ends up being the energy suddenly leaving the capacitor in the form of a current leaving the capacitor. And we'll talk about current actually in the next chapter. So we can figure out how much energy that is stored in the plates because we know the relationship between potential and potential energy. And we developed an equation for the change in potential in the previous section, right? So simply to find the change in potential energy, all we need to do is multiply by Q, right? Q times delta V will give us that energy change. To calculate the change in potential energy, we will examine delta V, okay? And we're going to replace it with the average value of the potential difference during the charging process, okay? So plugging in now the average potential during the charging process into the energy form, we can define the starting potential, the final potential divided by 2 as the average potential difference. Well, if when we start the charging process, we begin with an initially uncharged capacitor, Q will be 0 because it's uncharged. And so then the starting potential difference will be 0. Okay? And then when we're done charging the capacitor, the final potential will be equal to C equals QV. I'm sorry, Q equals CV. I always get that mixed up. And we can plug in these, basic values inside. So we end up with 0 plus V over 2. And multiply that by the Q in the energy equation, you get 1/2 QV. And so how does this fit in here, right? Well, it turns out this 1/2 QV is the most basic form of the amount of energy in a capacitor. And if you replace Q equals CV into that equation, you get a second equation for the change in potential energy of a capacitor. If now instead you plug in V equals Q over C into here, you get a third form of the change in electric potential energy of a capacitor, okay, as it's charging. So we have 3 energy equations, and they're all equivalent since they're all kind of obtained from each other. And this represents the energy that is stored in a capacitor while we're charging it, okay, until it's fully charged. So these 3 right here. And the equation that you use, it doesn't really matter. It's whatever fits the problem. So what you'll notice, these slides tell you, but you don't need to worry about it too much, is that this final form, Q squared over 2C, is actually a very similar form to the potential energy stored in a spring. And so the capacitor, energy in a capacitor is analogous to the energy stored in a spring. So let's do this example. And this is a really cool one because it's interesting to think about these really important medical devices in terms of the physics knowledge that you now have. Okay, so we have a defibrillator, and a defibrillator is essentially a capacitor. And that capacitor is charged in its little unit, right? And you see them they charge it up, they say charge, and then they pick up the paddles and they rub them together, and then they say like clear, to make sure you're out of the way, because they take those two paddles, which are like the plates of the capacitor, and then they stick them to the human chest to discharge, okay? So the question is, how much charge does the defibrillator have if the capacitor that charges the defibrillator is 80 microfarads and the potential that's applied is 2.5 kilovolts? Well, the fundamental equation for a capacitor is Q equals CV, right? Where the amount of charge on the plates is equal to the capacitance times the amount of potential on the plates. So we can certainly plug in our values here. C is 80 times 10 to the minus 6 farads. And then V is going to be 2.5 kilovolts, which is 2.5 times 10 to the 3 volts. Multiply those guys together. And we get 0.2 coulombs, which is actually a lot of coulombs, right? One electron is 10 to the minus 19 coulombs. So to get on the order of 0.2, I mean, that's a heck of a lot of electrons, right? So how much energy is being delivered to the human chest in this situation? Hopefully straight to the heart, right? But of course, some of it's gonna not make its way to the heart. So just because you're applying it to a general area over the chest. So how much energy is being delivered here? We can use any of those three equations since we have, options. We do 1/2 QV since now we know Q and we were given V, right? Similarly, we can do 1/2 CV squared or 1/2 Q squared over C, right? Either one would work since we have all three parameters. So let's just do 1/2 QV. Q is 0.2 coulombs. V is 2.5 kilovolts. So how many joules is that going to be? $250 joules. 250 joules of energy. It's actually quite a lot. So there's some, in these examples, right, there's a lot of information provided after it. There's some interesting thoughts, reflections, okay? I thought this was really cool. So the American Heart Association recommends that between 40 and 360 joules be applied to be effective. And of course, the person applying the defibrillator would probably have some knowledge of how to dial it up or down depending on the person's weight or body fat percent, estimation, of course, right? Because these are done in emergency situations. You don't really have a time to calculate someone's body fat percentage, but you can kind of take a look at them and get an idea. And that's going to affect how much energy you put in, because the energy and the current, I used this word before, current is the flow of electrons. It's going to depend on like what materials it's passing through. So you may need a lot more joules for someone that is, has more meat on their bones than maybe a child. So I thought that was just very interesting. And so let's do these conceptual questions. These are great. These are, again, like the questions I was telling you about earlier, where we're looking at the dependence of all these parameters that have to do with the capacitor and what happens when one increases and what happens when one decreases. And these are great test style questions. So I would really focus on understanding these completely. So let's say that you increase the distance between the plates of a charged capacitor, but you do not change the amount of charge, okay? So we're increasing D, and we are keeping Q constant, okay? What will happen to the energy stored in the capacitor? So we have U equals 1/2 QV as our fundamental equation for the energy. But we need to involve D somehow. But we also need to keep Q in there because we need to see it remain constant. And so the equation that I would use would be 1/2 Q squared over C. Because Q can be held constant here, and it's very apparent how Q is related to energy, and we can manipulate C. So let's first take a look at C. So C is epsilon naught A over D. So if D increases, what happens to C? It decreases, right? And so now we bring it over here into the energy equation. If C decreases, then U increases, right? Because it's inversely proportional. And Q is held constant. So we can see that the energy will increase if we increase the distance between the plates while holding the charge constant. So, oops, there's the answer. Let's look at this one. Suppose you increase the distance between the plates, okay? So D is increasing again. But now we're holding the potential difference constant. What would happen to the energy stored in the capacitor? So let's follow those same steps. Let's take a look at an energy equation where both capacitance and potential are involved, because we want to see how the potential is represented in the equation so that we can know it's being held constant. So the third equation for energy is 1/2 CV squared, right? Previously we used 1/2 Q squared over C because we wanted to see the charge. Now we want to see the potential being held constant. So again, let's compare what happens to the capacitance first as we increase D. Well, as D increases, we saw that capacitance decreases. So if capacitance decreases, then the potential energy will also decrease because they are proportional, right? And this is being held constant. So it will decrease. And so the problem-solving strategy here is that when you are doing these relationships, you need to make sure that you are seeing all of the variables involved. For example, what if instead I decided to use 1/2 Q squared over C, okay? Well, embedded in Q is a relationship with V, right? So, and I don't know that Q is being held constant. All I know is V is being held constant. So if I do my same relationship here where C is decreasing, I don't know how V behaves as a function of Q. I'm going to get the wrong answer, right? Because I can't see V. I need to see V. And so, well, what I need to do is to start with this equation, I would say, oh, well, Q is CV, right? So if Q decreases and V is being held constant, I'm sorry, if C decreases, I want to get my C's and Q's mixed up. If C decreases and V is being held constant, well, then Q must decrease as well, right? So I have a decreasing squared in the numerator and a decreasing in the denominator, and that's going to end up with an overall decrease. Why? Because this decrease is being squared and this decrease is only to the 1 power. So this one in the numerator is going to be more powerful. It's kind of a complicated way to do it, right? So you don't want to do it that way because Q and V are dependent on each other. So if you can't clearly see one variable, it's going to be hard for you to remember how they're dependent on each other. Okay, so that's why you want to choose the energy equation that is showing you the variables that are being manipulated in the problem. Okay. So we saw that charged capacitors store potential energy, and the amount of energy that's stored is proportional to the square of the charge on each plate. It's also proportional to the square of the potential difference between each plates, right? Because we saw 3 different equations for for energy stored. So in this final section, we're going to be kind of looking at capacitance in the context of circuits, okay? And in a circuit, it is advantageous to combine capacitors together. So we're going to be calculating what happens if we combine a bunch of capacitors together, okay? We can calculate the equivalent capacitance of a combination of capacitors. So to think about what we're doing, consider this analogy, okay? Let's say that you need to move a really heavy table across a room. Well, 4 people with regular normal strength could move it, or maybe 1 really strong person could move it. What we would say and how to describe that really strong person is we could say, well, that strong person has the equivalent strength of 4 people, or that those 4 people have the equivalent strength of 1 really strong person. And when you combine capacitors together, they're in certain orientations, their equivalent capacitance can change. And we're going to look at 2 specific types of ways you can combine capacitors. The first way you can combine capacitors is in series with each other. So you can think of this as kind of like the capacitors holding hands. So if you and 3 other people are facing forward, okay, and you decide to hold hands, well, you're going to see that this person's, let's say they're looking at us, right? So this person's left hand is going to be holding the right hand, and then this person's left hand will be holding this right hand. And if we consider left and right as positive and negative, you can see that when capacitors are put together in series, you have the negative side of one capacitor touching the positive side of another, okay, and so on and so forth. And the positive side of the battery and the negative side of the battery, right, determine what charge is on the ends. And well, the question is, what is the equivalent capacitance of an arrangement like this, which we call a series arrangement? They're somehow equivalent to 3, but in what way are they equivalent? Well, in series, I'm just skipping because I kind of already explained that. In series, what we note, and this is important, is that the charge on each plate is constant. So in series, the charges on each plate are the same, okay? And that's an important condition because that's going to help us figure out what the total capacitance of the arrangement is. So if we substitute what we know for Q, then what we can say is that the charge on each plate is equal to the capacitance of the first capacitor times the voltage across the first capacitor, capacitance of the second one times the voltage of the second one, and the capacitance of the third times the voltage of the third. And that's because they all have the same Q, right? We said that they're all equal, that Q is equal for capacitors in series. And if we do that, and if we solve for the potential V, we can see that the potential of each one is Q over their individual capacitances. And the way that we add capacitors or objects in series is we add their potentials together. And so when we do that, we can factor out the Q and finally come up with a statement that this guy here is equal to 1 over the equivalent capacitance, okay? So I kind of just went over a derivation with you, and I kind of just went quickly. If you want to do this derivation yourself, you can follow these math steps, but what you really need to know about the derivation is these boxed, that capacitors in series share the same charge on each plate. When you add capacitors in series, you add their voltages straight up. And combining those 2 ideas together show you that the total capacitance of capacitors arranged in a series arrangement is simply equal to the inverse of each capacitor added together, and then that itself is inversed, okay? So the second way you can add capacitors is not as complicated as this, okay? I think once you start working with and doing these little examples related to series and parallel, it'll start making more sense. But these are the relationships that you should recall, okay, and know very well. If the derivation of this equation is not making sense, that's okay. So the second way you can add capacitors together, okay, there's only two ways. It's either series, and then the second way is in parallel. So when capacitors are joined in parallel, you can think of them as someone holding hands face to face, right? This is the back of their head. This is the front of his head. And so that way, their left and their left hands are connected together, and their right and their right hands are connected together, right? And then take a look at this capacitance. So all the positive parts of the capacitor are connected to each other. All the negative sides of the capacitor are connected to each other. And this is all connected to the positive side of the battery, and this is all connected to the negative side of the battery. Okay, so there's two ways you can hold hands with somebody, right? You can hold hands with them when you're all facing the same direction, or you can hold hands with them if you guys are facing each other. And the hand that you hold of that person is either the opposite hand of yours or the same hand of yours, depending on if you are looking at them or side by side. So these are just the two different ways you can configure an object that has two arms, okay? And in this case, the object is a capacitor and not a person. So now we can go through a quick derivation of what is the total capacitance of three capacitors in parallel. Well, what you need to know about capacitors in parallel is that instead of the charges being equal, now the potential is equal for each capacitor, okay? So capacitors in parallel, they all have the same potential. And we can plug in our relationship that we know, our fundamental Q equals CV relationship for Q. The V's are all going to be the same, okay? And we can do our little derivation where we add them together, and we see that capacitors in parallel, the equivalent capacitance is simply equal to the sum of each capacitor, okay? So capacitors in parallel, a little bit easier to digest. Their equivalent capacitance is C1 plus C2 plus C3, okay? So recall what I wanted you to focus on about capacitors in series versus in parallel. They have different behaviors, different properties. In series, they have the same Q, right? In series, Q1 equals Q2 equals Q3. However, in parallel, the Q's are different, but the voltages are the same. Okay, Q is different. And in here, V is different. Okay, so they have different properties depending on how they're arranged. And those properties are how is Q related to each capacitor and how is V related to each capacitor. So let's do an example. If two capacitors are connected in series, find their equivalent capacitance for the case when capacitors have C1 equals to 2 microfarads, C2 equals to 4. And for the case where they both have 2. Okay, so we have series capacitor. So we have two capacitors. Remember, that's how we draw one in kind of circuit diagram form. They are connected in series, so that means they're holding hands next to each other. So the positive side is connected to the negative side, okay? So this is a series capacitor. This is C1, this is C2. And how you add series capacitances, well, the inverse of their equivalent is equal to the inverse of their sum, okay? So we plug in 2 microfarads and 4 microfarads, and let's do the math. So 1 over 2 plus 1 over 4. I can kind of do like, so that's actually 2 over 4 plus 1 over 4, right? Which gives me 3 over 4 microfarads, right? My farads are in the denominator still. So don't accidentally move them up here. That's a very common algebra mistake. They're still in the denominator. Why? Because what I'm finding is 1 over the equivalent capacitance. So I'm going to need to inverse this number to get the actual capacitance. So C equivalent is going to be 1 over 3/4 microfarad, which is equal to 4/3. And now my microfarad unit is in the numerator. So what I can see is that it's equal to about 1.33 microfarads. That's the equivalent capacitance of a series arrangement. Now, what if we have a series arrangement, but we have C1 equals C2? So this is C1 is 2 and C2 is 4. So now what if C1 equals C2? So let's start over. 1 over C equivalent equals 1 over C1 plus 1 over C2. Well, they're both equal to 2 microfarads. And that gives me 1 microfarad, right? 1/2 plus 1/2 is 1 over 1. I'm going to inverse that, right? C equivalent is going to be 1 over that, which is simply 1. And so what you'll notice is that the equivalent capacitance is smaller, right? So let's look at part B. I should have made a little bit more room. Let me copy and put this over in a separate page. Okay, that's part A. Part B is in parallel. Let's do the same thing if they're in parallel. Compare. So in parallel, what does it look like? Okay, in parallel, if this is the plus side and this is the minus side, well, it's connected to the same side as the other capacitor, okay? It looks a little crooked. Let me try to make it less crooked looking, okay? Right, there they are. Make this a little bit more. There we go. I'm screwing this up. Let's see if I end up editing this out. I just wanted to make it look, it was looking a little crooked and it was driving me nuts, okay? Plus touching the minus, plus touching the plus, minus touching the minus, okay? This is parallel. This is C1, this is C2. So let's find C1 is equal to 2, C2 is equal to 4. So now when we add the capacitors in parallel, life is much easier, okay? They add together straight away. So we can see off the bat it's going to be 6. So capacitors in parallel, when they add up, oh, I wrote 6 while I was talking. When they add up straight together, and you end up with a much larger capacitor, okay, than when they are in series. Look at it in series. Remember, it was 1.33. Now, that same arrangement, but in parallel, is 6. And so you can see how, like, you might imagine in a circuit board, you need a certain value. You may, and you only have 2 capacitors, right? You can just choose to arrange them in series versus in parallel if you need like a lower capacitance, or if you need a higher capacitance, you might want to choose to put them in parallel. Excuse me. So that is for C1 equals 2 and C2 equals 4. So if they are equal to each other, then, well, we're going to get 4, right? Because we're adding 2 plus 2. So, and that's for C1 equals 2 and C2 equals 2. All right, so in both cases, when you add capacitors in parallel, you get a greater equivalent capacitance than adding capacitors in series. Okay, and that's the general rule. So let's go back to the lecture. Just not open here. And if we look at there we go, right? Connecting capacitors in series reduces the overall capacitance. Connecting them in parallel increases the overall capacitance. All right, what about this? Find the equivalent capacitance of 3 capacitors, and we have a mixed arrangement. What do we do? Okay, let's dissect this arrangement. C1 and C2, how are they connected? They are connected in parallel. Okay, so C1 is parallel to C2. What about C3? How is C3 involved in all this? Well, C3 is in series with the parallel arrangement of C1 and C2. So what do we call this parallel arrangement of C1 and C2? Well, it's the equivalent capacitance of C1 and C2. So maybe we should find the parallel first, figure out what that equivalent capacitance is, and then call that C12, and then find out how C1, 2, and C3 are connected. Okay? So we're going to do it in 2 steps. So the first step is find C equivalent 1, 2. And well, C1 and C2 are in parallel, so that's easy. Adding capacitors in parallel, you simply add their capacitances. And so we get 3 microfarads. So now what I would do is redraw the circuit, or redraw the arrangement. So now, instead of C1 and C2, I'm going to have a new big capacitor called C equivalent 1, 2. And I can see that it's connected in series with C3. So now I'm going to just find the equivalent capacitance of 2 capacitors in series, where one of those capacitors happens to be the equivalent of 1 and 2. Okay? So to find the equivalent capacitance of 1, 2, 3, well, we're going to use the inverses because we're in series. So 1 over C1, 2, 3 is going to be equal to 1 over C equivalent 1, 2 plus 1 over C3. So 1 over C1, 2, well, we saw that was 3. And then C3 is 6. And so we add those 2 fractions together. This is basically 2/6, right? So we get 3 over 6 microfarads in the denominator. Now when I inverse, so right, I want to do 1 over C equivalent 1, 2, 3. I'm going to inverse that. I'm going to inverse this side. And I'm going to get C equivalent 1, 2, 3 equals 6 over 3 microfarads, which reduces to 2 microfarads. Okay? So it's kind of like a puzzle. I actually love these. It takes some getting used to. As long as you have your rules straight, everything is very logical, right? It's very logical. If you have this arrangement, you follow this rule. If you have that arrangement, you follow that rule. The difficult part is knowing which part to hit first, right? And that's just going to take practice. And so the rule of thumb is to do the more complicated side first, right? And by complicate, I mean like, if you just look at this picture on its own, you kind of have like a cluster of them over here. And so, I want to kind of like take care of that cluster and turn it into like a more refined, looking series arrangement, right? So you want to kind of tackle the complicated or clustered or dense side first, and then keep going from there. So in this conceptual problem, we have two capacitors, C1 and C2, and they're initially connected together uncharged. And they're connected together in both either a series or a parallel arrangement. So if we connect them in the series arrangement to a battery, and if we connect them in a parallel arrangement to a battery, which capacitor, one or two, stores the most amount of potential energy? So we're going to need to recall the potential energy equations, right? And we might need them all. Figure this out. Oops, Q squared over C. So we also need to remember how a series arrangement behaves versus a parallel arrangement. So the way a series arrangement behaves is that Q1 equals Q2. So the charges on the plates of capacitor 1 is equal to the charges on the plates of capacitor 2. In parallel, the potentials are equal. Okay, so the potential across the plates of capacitor 1 in parallel is the same as that of capacitor 2. So the potential energy in the series arrangement, we're comparing capacitor 1 and capacitor 2. So let's look at the series arrangement, C1, C2. C1 is 1 microfarad and C2 is 2 microfarads. So if we take a look at this energy equation, okay, we want to see the parameter that is constant, which is Q, and we want to see C. So if C is small, right? If C is small, then U is going to be big. So C1 is going to have the greater the greater potential energy because its capacitance is smaller. Capacitance is in the denominator. And since the Q's are equal, right? If we're comparing U1 to U2, I'll write U2 down here, right? You can clearly see since the Q's are equal, we don't consider it. C1 is small, which makes U1 big. C2 is big, which would make U2 small. So C1 has the greater potential in the series case. Okay, so if we look, we can rule this out because here it says C2 for both series and parallel, and then here it says C2 for series, so we can automatically rule that out. So now let's compare the parallel case. C1 is 1 microfarad, C2 is 2 microfarad, and I'm going to use the other energy equation because I know that V is held constant. In other words, they're equal to each other. So I want to see that V, and I don't want to guess its dependence, right? So in this case, C is proportional to U. So if C is big, then U is going to be big. In this case, C2 is going to be larger, okay? Since C is proportional to U with constant V. So that would leave us, so we rule out part A, right? Because it's not C1 for the parallel case. And it looks like C is the correct answer. Series case is capacitor 1. Parallel case is capacitor 2. Okay. And that's what we have down here. So to summarize this section, which is the final section that we will cover in 17, whenever we have two or more capacitors that are connected together, you can connect them in either series or parallel or a mix, okay? When the equivalent capacitance is going to be calculated by examining which parts are parallel and which parts are series. If we have two capacitors that are connected in series, there's some special things that happen, okay? When they're connected in series, all the capacitors have the same charge. And the equivalent capacitance is less than any of the individual ones in that series arrangement. When capacitors are connected in parallel, okay, all of the capacitors have the same voltage, and as a result, the equivalent capacitance is greater than any of the individual capacitors. Okay? So that ends chapter 17, which is kind of long, and mainly talks about energy, right? Energy of electric fields, point charges, and finally energy in capacitors, which are special applications of electric fields.